Now we get to start the last chapter. We get to go backwards. We're going to now look at antiderivatives. In this first area, we figure out what antiderivatives, the introductory parts of what antiderivatives or integrals are all about. They're about areas. We have to look at the algebra of what areas are. How do we find areas under curves or algebraic functions? We're going to find areas. That's horrible. Area by approximation. All right, for example, what does that mean? If we were given this first function, one minus x squared, we know by looking at this graph that, and we're going to stay on the domain from 0 to 1. When x is 0, y is 1. When x is 1, y is 0. So as we see this is obviously a quadratic equation pointing down, shifted up 1. So it looks like this. But we're only going to look at the positive side. So our question is, what is the area under this curve? How do we figure that out? Well, there are about 5 or 6 different ways off the top of my head we can figure this out. But what we're going to start doing it is the basic formula for area that we have is base times height. Where base is the x value and the height is the f of x function of it. So we have f of x is the height times the value of x. But if we do that, if we did this, the area of this curve, the height is 1 and the width is 1. So it's saying it's 1. But what that represents is this picture, is this cube, this little box. But as you can see, the area under this curve is a lot less. So we have all this area here wasted. So how do we fix that? What we can do with the same picture now since we know the function is 1 minus x squared, what we can do is we can cut it in half. Now we can find the areas of both of these and add them together. But that in itself brings out another problem. Where, okay, the base, the x value is the width. Right now it's just 1. Here, our width, or base is 1/2. The base is also 1/2 over here. It's from here to here. The question now is which area do we use? Because we know the formula for the area of a rectangle. We can either take this area, which gives us a lot of wasted space there, or we could take this area, which we don't have enough here. which is what we call the upper bound and lower bound, upper sum, lower sum. The upper sum, because if we added both of these using the bigger number, the one that's on top of the whole thing, then our area will be overestimated. The ones that use here is called the lower sum. Well, if we use lower sum, we're going to have grossly underestimated, because we're going to be looking at this area, and there's no area here because the lower sum is on the right-hand side. We have to, in mathematics, you have to use something that's consistent. So if we use the let me look at the lower sum.
So we're only looking at
Well, that's what we have to look at. We have to look at both of them and see which one gives us the best answer. If we use the lower sum, that's going to be lower than the actual area. So it's which x value do we use? Do we use 0 or do we use 1/2 as our x value? If we use 0, then that's going to give us a rectangle that's too big. That's going to give us something that's too large. That's an upper sum. So our first x value will be x equals 0, and then our second x value will be x equals 1/2. Now, if we use the lower sum, then we use the other bound, the other end of this interval. We can't use 0 because that's going to give us a big one, so we got to use a smaller one. So we have to use x equals 1/2 and x equals 1. The problem with that is, okay, we can find the area of this, but when x is 1, it's 0. Why? Because remember, our function is 1 minus x squared. 1 minus 1 gives us 0. So our height is 0. So now you see our area, our true area, has to be somewhere between these two. We have this area here, or we have this whole area here. This is important. If you see that concept, you have to know. If not, then I have to go continue explaining it. You understand what I'm talking about? Plug in the formula. Because remember, the formula that we're looking for area, the formula for area is the base times the height. The height is your function. Because here's your base, that's the width, and then the height is how high it goes. So when x is 0, that's the base, our base is 1/2. That's how wide it is. How high is our rectangle? Yeah, in this one here, it's 1. So the base is 1/2. And the area of this first rectangle goes to 1. Same thing here. The base is 1/2. Now what's the height? When x is 1/2, I have 1 minus 1/2 squared, which makes it 1 minus 1/4, which makes it 3/4. So that gives you my height. So it's 1/2 plus 1/8 gives us 4/8 plus 1/8 are 3/8. So our area is 5/8. In this in this inner one, I have the area is, again, the base is 1/2. But from this one, that gives me this inside area. At 1/2, we know the area is 3/4. You got this from here. Plus 1/2 when x is 1. When x is 1, 1 minus 1 is 0. So this gives us 3/8. So the 3/8, the true area has to be between these two there. So lower sum, upper sum. There's another name what we use. Since this is written inside it, we call this inscribed. Because the inscribed will give us the lower sum. Why? Because we're missing this whole area up top here. We don't have enough. The outer one, if it's on the outside, this is called circumscribed. Circum simply means we circumnavigate the earth, you're going around the earth. And that's what this is. We're going outside, around the function itself. Okay, so we know where we're areas between 3/8 and 5/8. Can we get a better picture of this? Yeah, we can. What if we take the same picture and instead of cutting it into 1/2, we cut it into 1/4? So let's look at the lower sum and the upper sum. Right, the formula is base times height. Base times height, that's a horrible formula for it. Let's do something more mathematical. We use the same function here. It's 1 minus x squared. What exactly is our base? Our base is our width. Since this is our x value, we can use, well, the height is our function, and the base is our width, is the change of x. Because each one of these are now delta x wide. Delta x means x2 minus x1. So how wide are each of these the rectangles? Well, 1/4 minus 0 is what? 1/4. 1/2 minus 1/4. 1/4. 3/4 minus 1/2 is 1/4. So all of these are my delta x's. So delta x is my base, and the function itself is my formula. All right, so in this one, the area of my first part, I'm going to have 4 areas. I'm using the lower sum in this one, which means I got to use the numbers on the right-hand side. So I'm taking the numbers of x equals 1/4, 1/2, 3/4, and 1. These are my x's. So we have f of 1/4 times 1/4. Why is it 1/4 times 1/4? because all my delta x's are 1/4 wide. So it's going to be f of x times delta x. Delta x is 1/4, so it's f of x times 1/4. Then I add the next one, f of 1/2 times 1/4. Then I add the next one, f of 3/4 times 1/4. Then I add f of 1 times 1/4. Again, it's important. Why do I use 1/4, 1/2, 3/4, and 1? The reason I'm using these numbers instead of using 0, 1/4, because the other ones will use x equals 0, 1/4, 1/2, and 3/4. This one uses 1/4, 1/2, 3/4, and 1. Why are different x's? Why do I have different x's? Because this is the lower sum. This is the formula that's going to give us a number that's lower than the actual area, because I'm doing the rectangles inside the function. So if I'm using inside the function, I have to use the right bounds, and that starts at 1/4. Then I have to use 1/2. If I'm doing the upper sum, then I have to use the rectangles that go outside the graph. That goes with this. So I get my highest point for this upper one, I get it at 0. And then I go to 1/4, 1/2, 1/3. So in this other one, I'll have f of 0 times 1/4, f of 1/4 times 1/4, f of 1/2 times 1/4, plus f of 3/4 times 1/4. Making sense here? Because this is the very important. If you don't understand this part, you'll get everything wrong from here on out. You have to understand, if I'm looking at looking for a lower sum, this is inside the graph. So which rectangle in this interval, where's inside the graph? Since it's a decreasing function, I use the right side. It gives me a smaller rectangle. If it's upper, it's outside. Where's the upper? Where's the bigger one? It starts at this point, and that starts at 0. All right, understand it or not, I'm moving on. So when x is 1/4, I have 1 minus 1/4 squared times 1/4 plus my function f of x is 1 minus x squared. So it's 1 minus 1/2 squared times 1/4 plus the third one, it's 1 minus 3/4 squared times 1/4. Then 1 minus 1 squared times 1/4. One minus 1/4 squared is 1/16 times 1/4. 1/2 squared is 1/4. 1 minus 3/4 squared is 9/16 times 1/4. 1 minus 1, 1/4. So the first one, 1 minus 1/14 is 13/14. One minus 1/4 is 3/4. One minus 9/16. So 16 minus 9 is 7/16. And then 1 minus 1 is 0. See, don't use your calculators. Try. This is basic math. This is the reason why you need a calculator. Is the stuff you have to know how to do this in your head. I mean, put it away. I don't want to see calculators. This is just basic math. And that's the only way you'll learn. That's the only way you'll learn. I mean, why not just use artificial intelligence and have do all your homework for you? So does that. What do you think? It's junk is junk. So we have 13 times 1 is 13. 14 times 4 is 54. Or 56, I mean. 3 times 1 is 3. 4 times 4 is 16. 7 times 1 is 7 over 56. No, hold on, 60, 64. Yeah, it looks weird. Plus 0. So we have 13 plus 7 is 20/64. If we multiply by 4, then we have 12/64. 32/64 is, yeah, 1/2 or 0.5. Do the same thing here. So we have 1 minus 0 squared times 1/4. 1 minus 1/4 squared times 1/4. 1 minus 1/2 squared times 1/4. 1 minus 3/4 squared times 1/4. So we have 1 minus 0 times 1/4. 1 minus 1/16 times 1/4. 1 minus 1/4 times 1/4. 1 minus 9/16 times 1/4. So it's 1 times 1/4. 1 minus 1/16 is 15/16 times 1/4. 1 minus 1/4 is 3/4. 1/4. 1 minus 9 over 16. 16 minus 9 is 7 over 16. We'll have 1/4. 15 over 64. 3 over 16. 7 over 64. So 15 plus 7 is 22 over 64. The first one has to get multiplied by 16 over 16. The next one is 4 over 4. So we have 16 over 64 plus 12 over 64, which makes it 1234 50 over 64. So this one here is 32 over 64. This one's 50 over 64. Remember, the area has to be between those two. Nothing is difficult here. This is stuff we did in third and fourth, second and third grade, actually. So our true area is between there. There's another example. Oh, actually, yes. Is there another way we can do it? We can make this better. How? Because these are still pretty far apart. 32 over 64, 50 over 64.
Are you?
Yep, because you notice from when we have two divisions, we had what? Our areas were 3/8 and 5/8 with only two divisions. With four divisions, we had 32 over 64, 50 over 64. So what would you do next?
Slice.
Keep it slicing up, yeah. So instead of 4, we'd have 8.
But then what do you do? Even though you don't.
Well, yeah, but again, you have to understand, you have to know what you're doing first. Computers and everything are trash unless you know what trash in, trash out. You have to understand what's going on. And again, you can't, Excel doesn't know how to do this. You have to program it what to do. So again, you have to know this stuff. And then again, how will you know if your formula is correct? You have to do the numbers yourself by hand. If you ever take a programming course, the first thing they teach you is always do a program and then put small, simple data in there that you can verify and then increase it from there. So that's what it is. This one? No, here I had 15 plus 7 is 22. Yeah, so once instead of 64s. Yeah, so the next thing we would do, yeah, we'd increase the number of our delta X would become smaller and smaller and smaller. But there's a third method. There's a third method we can use. Let's keep it at fourth. Because if we did the upper sum or the lower sum, we wasted too much space. There's a third method we can use. The midpoint method. What do you think this one is? Because we're going to still keep our delta X as 1/4. We're keeping our delta X 1/4. But what changes now are the X's that we use. Instead of using 0, 1/4, we'll now use the midpoints of all these intervals. Why would we do that? Let's see what happens here. Let's look at this top one here. If we use the midpoint, this is at 0, this is at 1/4. If we use the midpoint, we find the y value at that midpoint. Now the rectangle looks like this. How is that a better alternative? Let's compare this one to the other ones we just looked at. If we used this one at 0, when x is 0, look at all this waste there. If we used x is 1/4, look at all this area we don't have. So this one up here is overestimating, this one here is underestimating. We either have too much waste or not enough idea. But if we do it this way, this area and this area start canceling each other out. So the area here is much bigger than these two put together. This underestimate here, again, is a lot larger than this one. So the midpoint method is the preferred method. So our x values, how do you find the midpoint between 0 and 1/4? Divide what by 2?
0.
Okay, let's do it. So what do you do with those? What's the midpoint between 1/2 and 3/4? Ah, there's what I'm looking for. In order to find the midpoint, you take your 2 points, divide and add them together and divide by 2. So for the first one, it's 1/4 divided by 2, which becomes 1/8. So that's my first x. My first x I'm going to use is 1/8. Then what's my next x value? So I'd go from 1/4 plus 1/2 divided by 2. So this is, I need 2/2 there. So it's 1/4 plus 2/4 is 3/4 divided by 2, which becomes 3/8. There's actually a faster way you can do this. Can you guess what it is? Ooh, not 1/8.
Not the midpoint, but 1/2 of 1.
Add the delta x size. Because from the beginning to the end of each interval is 1/4. That means the midpoint to midpoint should also be 1/4. So start off with your first midpoint, which is 1/8. Add 1/4 to it, which is 1/8 plus 2/8, which is 3/8. That's what we got there. So 3/8 plus 1/4, or 2/8, is 5/8. And then 5/8 plus 2/8 is 7/8. So those are your x values. So now our area calculations are going to be f of 1/8 times 1/4 plus f of 3/8 times 1/4 plus f of 5/8 times 1/4 f of 7/8 times 1/4. So it's 1 minus 1/8 squared times 1/4. 1 minus 3/8 squared times 1/4. 1 minus 5/8 squared times 1/4. 1 minus 7/8 squared times 1/4. 1/8 squared is 1/64 times 1/4. 1 minus 9/64 times 1/4. 1 minus 25th over 64 plus 1 minus 49 over 64. So 64 minus 1 is 63 over 64. Sixty-four minus 9 is 55. Sixty-four minus 25. 64 minus 25 is 44. 39 over 64 times 1/4. And then 64 minus 49 is 15 over 64. Since they all have 1/4 next to it, we could just factor out the 1/4 and just add all these other ones. So we have 63 plus 55 plus 39 plus 15 all over 64. Plus 39 plus 15. $172 over 64. And now we use calculator because now it's getting bigger. Actually, we'd simplify that, but only got half an hour left. $172 divided by 64 is 1/4 times 2.6875 divided by 4 is 0.672. Remember, earlier we had 32 over 64, which is 0.5. Now we have 0.67. And the other one was 50 divided by 64. 0.781. So this is our lower sum, this is our upper sum, this is our midpoint. So which one is our area closest to?
Close to 0.67.
Yeah, it's somewhere there.
I make a shortcut. Lower and divide that by 2.
Good thinking, but no. ¿Por qué no? Why not? The reason not, the reason it's not is because of the nature of the curve. Right. Because this upper bound, again, you don't see exactly how much is above there. And same thing with the lower bound. You don't see how much you're wasting. So you can't really take that, which is even reason why the midpoint isn't accurate. Because is this curve going to fit exactly here upside down? No. So, I mean, that's just why, because of the nature of the curve itself. Good thought about that. I said, let's find a shortcut. So, but we can look at more ways of trying to find this thing, but that's the only way we can get better. The only way that can get better is by increasing the number of making your delta X go to 0. Ooh, I just let the cat out of the bag here. Where have we seen this before? When we talked about limits. When delta X goes to 0, then we'll have the true area. That's what we're shooting for. That's what our eventual goal is for getting this to where we're going. Now, that we can figure out the errors of these things. We have an error magnitude. The error magnitude is the absolute value of the true value of this area minus the calculated value. Put your phone away. Is your phone or your calculator? Okay. Now, the problem is, do we know the true value? No. So that's unless we're given the true value of this area we're looking at, we can't really calculate this. The calculated value is what we did. That's what with any of those methods that we have. The error percentage is the error magnitude divided by the true value. So if you're given the actual true value of the area or the value whatever you're looking for, you can calculate the errors, how far you're off from using your method. Because if you think the percentage is too high, then think of another. I mean, as we said, instead of 8 intervals, let's go to 16. Let's go to 32. Let's go to 100. And that's going to make the error percentage smaller and smaller and smaller. Eventually, we want those to go down to 0. So far, so terrible. No, the reason you're absolutely correct. Yeah, using calculators we say, but we just did basic math there. You didn't need to use calculators.
No, but I make like those errors. When I plugged in the homework assignment, it doesn't give credit like the old yet. Okay, the old
I thought I did.
is younger than the age that I last took calculus, but when I last took it, somebody like you would give me credit for.
And that's true. In the old days, yes, when we had things turned in,
Yeah.
oh, that's pretty close, yes. But yeah, that's why I hate technology and online learning, because unless it's exactly the format they want it and the digits and everything, you get it right. If the answer is,
On this,
and that's why I hate it. That's why it's No, it is because you can't avoid it. But that's part of the limitations that put in there is it's only as accurate as the technology that we have. And what its essence is doing, it's making the US drop lower and lower and lower in the intelligence scale than the rest of the world.
So did you propose a solution?
Well, in reference to the experiment I was doing, yes, but not in general. That's the general topic. That's out of the scope of that. So that's just further research I got to do and do presentations, conferences. And I'm not the only one. I mean, it's pretty much universal that technology is ruining our brains.
How we done? And my brain is so different now and it's like, I did the same brain.
It's just no, it's I've seen so many students go in tears. If the actual answer was 2.71 and they put 2.72, they get it wrong.
Yes.
No ifs, ands, or buts. And they go into tears. Why? Because they did a rounding error long time ago. And so it's horrible. And
Margin of
you would
error,
think.
that's as good as the software. Like the coder should give that little margin of error, like what are the possible answers that are acceptable?
Too much coding, too expensive. Remember, the more code you put in there, you have to test. The more you put in there, you have to pay somebody to do it. And it's all a matter of money. Back in the old days, all you do is whoever wrote the book, that's all you have to pay. The rest of it was teacher grading. So yeah, I totally agree with you. Is because of that, we are over dependent on the technology we're using. And because of that, we're skyrocketing, I mean, nosediving straight into the ground with our intelligence. Oh, let's look at this. Section here is distance traveled. Whenever you deal with distance, what's the formula for distance? How fast you're traveling and for how long. So it has to do the same thing, is you start off at time equals 0, and then you move on at certain intervals. This is time 1, this is time 2, this is time 3, and this is this is time 4. It's the same thing. We can keep on going to infinity, but we have each of our delta t's are defined inside there. So now, how do we define rate? Because all of these obviously are functions of time. Distance is a function of time. Is rate a function of time? Prove it. No. When you drive, do you drive steady? When you look at your speedometer, what do you know? How do you read that? If it's 30, well, how do you read that? Per hour. So yeah, so it's the distance per time. So rate is a function of time. When we first started in chapter 2, we did that motion problem of the rocks and everything. And then we talked about the first derivative of position function is your velocity and everything. So here we're looking at the velocity of the object. And the time, since we're looking at time intervals, we're looking at delta t there. So the complete distance traveled is a function of t, which is equal to the distance equals the velocity at time 1 times delta t. plus the velocity at times 2 times delta t plus the velocity at times 3, and so on and so forth. The velocity at time n delta t. So that's how, we use the same thing no matter whether it's up or down, left or right. It doesn't matter how we're moving. It's just that for this level, we won't deal with diagonal flight or non-horizontal, non-vertical. Because if it's horizontal and vertical, we don't have to worry about calculating the sine and cosine of the object moving. So here's our example. Example 1. The velocity function of a projectile fired straight up is f of x, or f of t, since we're dealing with time, is 160 minus 9.8 t meters per second. How do we know that it's going to be 9.8 meters? How do we know the units are going to be meters per second? How do we know it's metric?
Meters.
Well, no, if that wasn't there, how do we know it was going to be metric? Very good. We talked about that first week of class also. In metric, gravity is 9.8 meters per second. In the SAE, gravity is 32 feet per second. So this, since gravity is a force pulling down, you notice what's happening here is even if the object is shot straight up, once the initial velocity is worn off, it starts flying. What's the only force acting upon it? Gravity. That's the only thing. So once this is the initial velocity, it takes off at 160 meters per second, or whatever. When it starts off at 160 feet, this is the only force acting upon it. So let's use it. Use how far will the projectile rise during the first 3 seconds of flight? Then that's question 1. Question 2 is how close do the sums come to the exact value of 435.9 meters? Now, the reason it said sums, because we have an option to do what? Remember with our first example, this is at 0, this is at time 1, this is at time 2, this is at time 3, and so forth. Each of those intervals dictate what delta t is. The reason it said sums is because we can calculate three different ways here. Can we? Yes. Remember the first one we had at 0, 1/4, 1/2, and so forth? Our first x's were at 0, 1/4, and 1/2. Then the second one we did it at 1/4, 1/2, 3/4. And then we went to the midpoints. 1/8, 3/8, 5/8, and so on and so forth. So in other words, we can take the lower bound, lower sum, upper sum, or the midpoint. And we can find which one's the best. Okay, so let's do it both ways. Let's look at, but in our case, the question said first 3 seconds of flight. So our time is going to be 1, 2, 3. So for the first one, let's look at our times being at 0, 1, and 2. Then the next time we're going to look at it, we're going to look at 1, 2, and 3. Then the third time we're going to look at it, we're going to look at it at 1/2, 3/2, 5/2. And the formula we're going to be using is 160 minus 9.8 t, and the delta t is looking like it's going to be 1. Because between the distance between any of these is 1 second, as you said earlier. Okay, so I'll tell you what, everybody in this room, pick a different t value to do. You only have to do 3 of these, so use your calculators, use your toes if you have to. I want to know the complete distance this object travels. So it's going to be f of t1 times delta t plus f of t2 times delta t plus f of t3 times delta t. The only thing different, this is t1, this is t2, this is t3. t1, t2, t3. Finished already?
I think so, I don't.
Which one did you do? You do 0, 1, and 2? Okay.
No, I know when I know something, and I don't know.
Right. All right, so here we have f of 0 delta t, f of 1 delta t, f of 2 delta t. And delta t for all these is equal to 1. What's that? You do this one? Okay. So at 0, we have 160 minus 9.8 times 0 times 1.
I did not do that on so that I got it all wrong.
Yes.
Just getting it that. Yeah, I think it was right.
And then 160 minus 9.8 times 2 times 1. Because remember, the formula itself is f of t times delta t. And delta t, we said, was 1. So f of t is this function here. You have to use this equation for each of your value t's. So we have 160 minus 0 times 1. 160 minus 9.8 times 1. 160 minus 19.6 times 1. Since they're all times 1, I don't have to worry about those. So 160 minus 0 is 160. 160 minus 9.8 is 150.2. 160 minus 9.6 is 0.4. It's 0. 140.4. Add those together. It's going to be 0.6, 2, 3, 11. It's 450.6 meters. So that's when t is on the left. We're using the left side there. Now let's look at the next ones where t1 is 1, t2 is 2, and t3 is 3. F of times 1, f of 2 times 1, f of 3 times 1. So we have 160 minus 9.8 times 1. 160 minus 9.8 times 2. 160 minus 9.8 times 3. Then they're all times 1. Minus 9.8. 160 minus 19.6. 29.4. So 160 minus 9.8 is 150.2. 140.4. 130.6. And 12. 1, 2, 3. Okay, so it's 10, 12, carry the 1, 1, 7, 12. Four 21.2. One, two, three, 4, 2, 1, 2. Unless I did something wrong here. This is 30.6. This is 40.4. This is 50.2. This just looks weird. This looks very small compared to this one up here. Okay, good. That's
And I did the wrong. That's
now,
on you then. It's interesting.
now the midpoint. So the midpoint we're using here is at T1 is point or 1/2 or 0.5. T2 is 3/2. And T3 is 5/2. So the distance traveled, again, delta T is still the same, that's still 1. So it's still going to be 160 minus 9.8 times 1/2 times 1. 160 minus 9.8 times 3/2. 160 minus 9.8 at 5/2. 9.8 divided by 2 is 4.9. 4.9 times 3 is 14.7. 4.9 times 5. 4.9 times 5. 24.5. So 160 minus 4.9 is 155.1. 160 minus 14.5 is 145.3. And then 135.5. 9, 15. It's 435. So we have 421.2, 435.9, and 450.6. Okay, and the next part of the question asked, how close do the sums come to the exact value of 435.9? In other words, here you can find the error magnitude and error percentage. Since we have the exact value, remember the error magnitude true value minus computed or calculated value. And then we have the error percentage, which is the error magnitude divided by the exact value. So we have the EM of the first one is 43.435.9 minus 421.2. That's 741. So it's 14.7. So the EM of the first one is 14.7. And the second one, it's 0 because it's exact 435.9. And the last one is 435.9 minus 450.6. We have 450.6 minus 435.9. 741. This 14.7 the other way. What do y'all think? Pretty straightforward. Once you understand what formulas to plug in there, it's for movement problems, it's always going to be the velocity or the distance formula. For anything else, it has to be given to you. Yeah, so it's pretty much everything else is. Oh, let's look at the trig function. Since we're here, let's look at a trig example. Since you all like trig so much. Estimate the average value of the function f of x equals sine x on the interval 0 to pi. Is it average? Yeah. So you guys are starting automatically. What do you need to know first? Well, first off, let's look at the graph of this thing. From 0, we have pi over 2, we have pi, we have 3 pi over 2, and we have 2 pi. But all we want is from 0 to pi. At 0, what is sine? 0. At pi over 2, sine is 1. At pi, it's 0. So we have this shape curve to deal with. The same problem we just had earlier. If we just leave it like this, cut it in 2 parts, it's pretty boring. If we cut it into 4 pieces, that's pretty boring as well. So for our delta x's, let's make our n 8 slices. So our delta x is pi over 8. Ooh, we never talked about how to calculate pi over 8, the delta x. Delta x is x2 minus x1 divided by n. How many slices do you want? How many intervals do you want, I should say? So from your the width of your interval, the second point minus first point divided by n. Well, since this one all we had was 0 to pi, our delta x was going to be pi minus 0 over 8. So we have pi over 8. That's our delta x. Now, what do we have to do from there then? What else do we have to do? We know the highest point is 1. So that's pi over 4. 3 pi over 4. That's only 4 pieces. We need 4 more. So our delta x is pi over 8. So from 0 to the first interval is pi over 8. That's 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8, and 8 pi over 8. That's the easiest way to determine what the values are. 0 to pi over 8. That's 1 pi over 8. Then 2 pi over 8 is 1/4, or pi over 4. Then 3 pi over 8, 4 pi over 8 is pi over 2, 5 pi over 8, 6 pi over 8, 7 and 8 pi over 8. So that's the easiest way to do the intervals. What do you have to do now? We're looking for the area. So we have our function times delta x. Since delta x is the same for all of them, we can put that out in front. So it'll keep us from having to write it over and over and over and over. Okay. Now the question is, do we use the lower bound or the upper bound?
Can we use the midpoint and it's more accurate?
Oh, we could. We could very well, we could have done that. So we have pi over 16 and then calculate each one of those. If you want to, we can. But there's another way we can do it. Oh yeah, we're just looking for an approximation. But you're right. That would be the ultimate best one. If we use the lower bound, the one that's inscribed, what's the area here? 0. So for us to get any value for this left side, we have to use the right endpoint. For this half of the curve, we have to use the right endpoint. What about the other half of the curve? Now we have to use the left point. Follow that? You have to understand what the graph looks like first, because if we just used the lower point or the right endpoint for all of them, then we'd have too much here, not enough here. What would that give us? It wouldn't be a good approximation. We don't know. Eventually, what would we do? And then we'd look at the midpoint. But for this, let's just look at this right now. Yes, you see what we're getting to. Eventually, we're getting to the point where our delta x will get a lot smaller and smaller and smaller and smaller. We eventually want it to go to 0. That's our ultimate goal. But first, we have to understand what's going on. So for the first one, our x value is pi over 8. So it's f of pi over 8. Then the next one is f of pi over 4. Then f of 3 pi over 8. Then f of pi over 2. So that's in the first half. Now the second half, we have to use the left side. So it's also f of pi over 2 again. F of 5 pi over 8 plus f of 3 pi over 4, and then f of 7 pi over 8. Remember, our function is sine x. So it's pi over 8. So it's sine pi over 8 plus sine pi over 4 plus sine 3 pi over 8 plus sine pi over 2 plus sine pi over 2 again, sine 5 pi over 8, sine 3 pi over 5 pi over 8, 6 pi, that's 7 pi over 8. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. So it's 5 pi over, oh, and 3 pi over, yeah, it's this one here. So 3 pi over 4 plus sine 7 pi over 8. Out of all these, only 2 of them are easy to do. Sine pi over 2. That equals 1. So what is sine pi over 8? That's when you need your calculator. Because it's going to be an intermediary point close to 0, or close to 1. Or close to 0.5. What is sine 5 pi over 8? Yeah, 0.38. Sine pi over 4. But remember, when you look at this thing, look at these numbers. So pi over 8. Pi over 8 is very small. The sign deals with the y values, so that's why it's 0.38. It's very close to 0. Sine pi over 4. It's over here. So that's 0.7 what? 71. 3 pi over 8. That's even further. The next two are easy. It's 1 and 1. So 5 pi over 8. Which actually should be the same as those other ones because of symmetry. So it's going to be 0.93, 0.71, 0.38. Add up all those together. .04 divided by, or times pi over 8. So 6.04 times divided by 8 times pi. You sure? Yeah, that sounds more like it. 3.37. Was 0.38, 0.71, 0.93, and 1. Add up these four and then times 2. No. No, it's not times 8. So remember, the question asks us find the average. So to find the estimated average, we take this, so the average is 2.37 divided by pi. Which is approximately what? Or it's 0.7576, yeah. Because that's the width of our whole things from 0 to pi. There's the end of that section. Trust me, the next, okay, this one, the first section and the second section are very drawn out and boring. You won't have to do those for long. Once we get to section 3, then it's all calculus based and it goes much faster. And then because all of these calculations right here, we could have done it in 2 steps by something called the Riemann sum. Once we use his theorem, because also, as you said earlier, what if we had 16 intervals? What if we had 32 or 64? Again, because of that, we have to look, our delta x gets smaller and smaller and smaller. Because of that, we have to look at limits of these things. So we have to, next time we'll introduce notations and symbols, and then we'll go into how limits fit into this whole thing. All right, everybody, we're almost done. We only have 5 more sections to cover. And think about it. We have 5 more sections, and we have 6 more days. But my goal is to finish everything next week. Yeah, because once we finish this next section, again, these are the hardest part because we have to drag out all the writing. Once we have the formulas, remember how fast we did chapter 4, chapter 3? When we started learning the formulas, it flew. Same thing here. Once we learn the formulas, the shortcuts, we can start doing calculations now. Right, well, that's it. If we're gonna finish next week, then the week of Thanksgiving, you don't have to show up. I have to be here. You guys don't have to. No, no more lectures. Because once I finish the last lecture, lecture's done. And then we have the week after that, then finals. Pretty much after next Wednesday,